Hello everyone, and thank you so much for your interest in my work on radar-based state estimation and mapping for visually degraded environments. This presentation will give an overview of my past work in this area, and it will lay out some of my planned research directions for the remainder of my PhD. I'm Andrew Kramer. I'm a PhD candidate at the University of Colorado Boulder and a NASA Space Technology Research Fellow. I'm advised by Chris Heckman, and I'm a part of his Autonomous Robotics and Perception group. Our group generally focuses on perception and state estimation and control methods that allow for long-term autonomous operation of mobile robots. My particular focus is on state estimation and SLAM methods for perceptually difficult environments. Now, as I'm sure many of us are already aware, SLAM, or simultaneous localization and mapping, is the problem of concurrently estimating a robot's state and a model of its environment. In the simplified example shown, we would need to estimate both the poses of the car and the locations of the mugs over time and relative to some global reference frame. Now, SLAM is a core competency for autonomous mobile robots operating in unknown environments. Without the ability to create a model of the environment and localize within that model, higher-level functions such as path planning and exploration would be impossible. Now, SLAM methods exist for a broad range of sensors, including 2D cameras, depth cameras, LiDAR, GPS, and inertial measurement units. Many of these can be used in single-sensor SLAM methods, and arbitrary combinations of them can be fused in multi-sensor methods. Now, these often work beautifully when conditions are favorable, i.e. when the air is clear, ambient light is plentiful, or the robot has an unobstructed view of the sky. However, there are very few SLAM systems designed for less than optimal conditions, and none that are naturally suited to handle a broad range of perceptual challenges. Such a SLAM system is badly needed, too. From exploring subsurface caverns on the Moon, to navigating the dusty surface of Mars, or foggy environments like Venus and Titan, to exploring visually chaotic environments like the Comet 67P Churyumov-Gerasimenko, autonomous robots using the current state-of-the-art in perception face large, often insurmountable obstacles from visually degraded environments. This is why the goal of my PhD research is the development of robust methods for state estimation and mapping in visually degraded environments. Now, to underscore the difficulties of state estimation in visually degraded environments, I'd like to present my earlier work on visual inertial odometry for subterranean environments with no ambient light. In such an environment, a robot using VIO must bring its own light source. This violates a key assumption in visual odometry, that the illumination, and therefore the appearance of the scene, is constant and independent of the robot's state. This is referred to as the brightness constancy assumption. But when carrying an onboard light source, the appearance of the scene is heavily dependent on the robot's pose. This causes many undesirable effects, such as illumination drop-off, where surfaces near the camera are well lit, but more distant surfaces receive quadratically less illumination. Another concern is shown here, where a small, brightly lit portion of the scene throws off the exposure for the rest of the image. Lower light levels also necessitate the use of lower shutter speeds, making motion blur a big problem. And lastly, direct lighting can easily cause specular highlights, as seen along the right edge of this image. All of these factors can cause the appearance of a visual landmark to change between observations, significantly complicating the data association problem. Now, to address this, I created a custom stereo visual front-end for OKViz, a popular visual inertial odometry package. My goal was to make better use of the available information in an actively lit subterranean environment. Now, the stock visual front-end in OKViz, pictured here, is able to accept inputs from multiple cameras, but it treats these cameras as independent, and it doesn't assume any overlap between their visual fields. So even if both cameras observe the same landmark, OKViz treats these measurements as independent monocular measurements, parameterized by the projected positions of that landmark on each camera's sensor. My stereo front end, on the other hand, assumes the cameras will have overlapping visual fields, and it explicitly associates key points between the two cameras and parameterizes measurements by the projected position of the key point on camera 0 sensor and the depth of the key point calculated via stereo triangulation. This gives the system an additional source of information when associating new measurements to existing landmarks. which helps in cases when the appearance of a landmark may change significantly between observations. This means the system is better able to discriminate between correct and incorrect associations, increasing the number of correct landmark observations in each frame. Now, I tested this development on a novel subterranean visual inertial dataset collected by my former lab mate, Mike Casper. In this dataset, a handheld sensor rig with an onboard LED headlight was carried on a 340-meter out-and-back course in the narrow tunnels of the Heidi Gold Mine in Central City, Colorado. The same run was repeated with the onboard light set to 2 different intensities. Now, I evaluated my stereo front end's performance on this data against the performance of the stock multi-camera front end from OKViz. For these tests, performance was parameterized by the total translational drift accumulated over the entire course. Now, the translational errors for my stereo front end are shown here in the box plots labeled plus depth, and the errors for the stock OKViz front end are shown in the plots without that label. Curiously enough, the errors when using the stock OKViz front end are lower than those for my stereo front end when the onboard headlight is set to higher intensity, but the errors are actually even smaller when using the lower light setting. Further, errors for runs with my stereo front end are lower than those for runs with a stock OKViz front end in the low light tests, and my stereo front end in low light consistently provides the lowest translational drift. Now, I hypothesized this counterintuitive result is due to a better distribution of key points with lower intensity lighting. Higher intensity lighting results in a sharp drop-off in brightness, so even though more key points may be detected under more intense lighting, those key points are distributed within a very narrow range of distances from the camera, as shown in the picture. With the headlight set to lower intensity, indirect lighting from reflections and so forth is a stronger effect, and the brightness drop-off isn't as pronounced. So even though fewer key points may be detected under low intensity light, these key points are better distributed throughout the scene and are thus more informative for visual odometry. Now, this is an interesting result, but the project also highlights the need for robotic perception and state estimation methods that are robust to these sorts of visual challenges. Now, I believe a perception system based on radar would fill this need. Radar doesn't require ambient light, and it's unaffected by airborne obscurants like dust, smoke, and rain. A SLAM system that uses radar as its primary sensor would therefore be robust to many of the most difficult perceptual challenges faced by autonomous robots. Now, the rest of this presentation is going to be organized as follows. First, I'll briefly discuss some basic radar theory, and I'll also give some attention to radar remote sensing, as this is important for one component of my planned work. I'll then give a brief review of my work up to this point in radar-based state estimation and mapping, and lastly, I'll detail my planned research directions for the remainder of my PhD. Now, to discuss robotic perception with radar, it's necessary to explain a little bit about how a radar sensor operates. As shown in this figure, the radar's transmitter first sends out a pulse of RF radiation with linearly increasing frequency, referred to as a chirp. Now, if we assume there is a single point scatterer in the environment, the chirp will reflect off that scatterer, and the reflection will be detected by the radar's receiver as a time-shifted version of the transmitted chirp. The received chirp is then subtracted from the transmitted chirp to create an intermediate frequency, or IF signal. The frequency tau of that IF signal is proportional to the time of flight of the chirp. So if there is only one scatterer in the sensor's field of view, determining that IF frequency is pretty trivial, but in the real world there will be a large number of scatterers as well as additive noise sources, and we want to determine the contribution of all of the scatterers in the environment to the received signals. So to do this, we take the Fourier transform of that IF signal to convert from the frequency-time domain to the power-frequency domain. The largest peaks in that Fourier transform will correspond to the strongest scatterers in the environment. Now, in a real radar scan, the Fourier transform signal will look a lot more like this. In traditional radar signal processing, we often want to segment out the strongest detections and ignore the lower power signals, which are more likely to correspond to thermal noise or so-called clutter. This is usually done with a constant false alarm rate detector, which identifies the strongest peaks in the transform signal. These detected peaks are returned to the user as a set of point targets parameterized by their range and intensity, and the rest of the information in that scan is discarded. Now, the radar sensor we're using uses this process to detect targets, but it also uses phase differences in the returns between multiple antennas to estimate the angle of arrival of those targets, and it uses phase differences between successive chirps to estimate the Doppler phase shift of those detected targets as well. Now, the robotics community often attempts to use radar much as one would use other more common range sensors like LiDAR, but this video will hopefully demonstrate why that's a bad idea. The video shows detected targets from radar scans in red, with LiDAR points in green as a sensor rig is carried through a parking garage. Now, it's immediately apparent that these radar scans are very different from LiDAR scans. They're much more sparse, for one. The radar returns at most 200 targets per scan, while the LiDAR returns tens of thousands. In addition, there's very little repeatability from scan to scan. The radar sensor may detect targets on ceiling beams, cars, or pillars, but the location of a detected target on those objects isn't consistent from scan to scan. And additionally, the use of the constant false alarm rate detector ensures that some of these targets will be spurious detections. So all of this hopefully shows that radar scans should not be processed in the same manner as LiDAR, and it's important to use radar in a manner that takes into account the unique physics of the sensor. Luckily, radar signal processing is a very mature field, and there's a lot of well-established work from which we can draw inspiration. For instance, radar has been used for more than half a century to create dense, detailed images like the one shown here. This is in stark contrast to those sparse, noisy scans that we saw on the previous slide. Now, the process used to create such imagery is called synthetic aperture radar, or SAR. SAR involves taking many individual radar measurements as the sensor moves over the scene being imaged. Instead of detecting discrete targets from these scans, the raw signals are transformed to the world frame, interpolated to a Cartesian grid, and then added together. These accumulated scans are then processed as if they were a single scan. And this allows a radar with a small antenna on a moving platform to mimic the properties of a stationary radar with an impossibly large antenna. This is called synthetic aperture radar because in the radar literature, antenna size is referred to as aperture. So not only can SAR be used to create extremely detailed imagery, depending on the radar bandwidth used, SAR can image through clouds, foliage, and even through solid ground to a limited extent. For example, on the left here, we have a visible light image of the volcano Klyuchevskaya Sotka mid-eruption. The image on the right was taken at the same time, but with SAR operating in the microwave range. Now, notice that the prominent ash plume in the visible light image does not appear in the SAR image. Now, SAR techniques have gotten very little attention from the robotic perception community. There's only been one use of SAR for 3D near-field imaging in the robotics literature of which I'm aware. It used millimeter wave radar to do 3D imaging of discrete objects like the coil spring pictured on the slide. Although this work is very impressive, it's not suited for robotic perception on mobile robots. For instance, in this work, to provide a priori knowledge of the alignment between radar scans, the sensor was positioned using a robotic arm, but this is clearly not a feasible solution for mapping on a mobile robot, where the alignment between radar scans is going to have a significant uncertainty to it. So later in this talk, I'll propose a method to do SAR-based mapping on a mobile robot with unknown scan-to-scan alignment. But right now, I'd like to discuss my first successful foray into radar-based state estimation, estimating the velocity of a sensor platform using radar Doppler measurements. Now, other methods for radar-based state estimation have been limited to a 2D environment, and they've also often relied on heavy and power-hungry radar sensors, such as the one pictured here. This makes these methods unsuitable for robots that must operate outside the planar world, and those that have limited payload and power capacity, such as microaerial vehicles. My work, on the other hand, is intended for use in a 3D environment. It uses a Texas Instruments AWR radar sensor, which is a lightweight, low-power system on a chip. This makes my methods much better suited to small, agile robots like the quadrotor drone shown on the slide. The AWR sensor uses a frequency-modulated continuous waveform, meaning that it can detect the Doppler velocity of targets in addition to their range and intensity. It also uses multiple transmit and receive antennas in a multi-input, multi-output architecture. This allows it to estimate the angle of arrival of reflected signals as well. Now, if we assume our sensor platform is moving and all objects in the scene are stationary, then the velocity of targets in the scene relative to the sensor has equal magnitude and opposite direction to the velocity of the sensor platform. A target's Doppler measurement is the magnitude of the target's velocity vector projected onto the ray between the sensor and target. So, if we have Doppler measurements of many targets distributed throughout the scene, we should be able to regress the velocity of the sensor platform. Now, this leads us to our Doppler sensor model, wherein the true radial velocity of the target, the difference between the Doppler measurement and the Doppler error, is the cross product of the estimated sensor frame velocity and the unit ray between the sensor and target. Now, it's important to note that the true ray between the sensor and target is the difference between the measured ray and the error in that ray. The Doppler error term actually includes the error in the target ray in addition to the Doppler measurement. This is because, unlike with LiDAR, there are going to be significant errors in that target ray, and these need to be modeled. In this case, the target ray error is both a state to be estimated and an error to be minimized. Using our Doppler constraint, it is theoretically possible to estimate the sensor platform's velocity using only the radar measurements taken at a single time step. But the characteristics of our sensor make this an inadequate solution. Now, the chief problem here is with the sensor's measurement of azimuth and elevation angles. The expected error for these angles is actually proportional to the magnitude of the angles themselves. So measurements with small azimuth and elevation angles are quite reliable, but these provide very little information about the sensor's velocity in the y and z directions. For this, we need radar measurements with larger azimuth and elevation angles, but these are inherently less reliable. So if we only use the Doppler constraint, our velocity estimates in the y and z directions are going to be significantly less accurate. This is why it's necessary to jointly estimate the system state at several time steps using IMU measurements to constrain the change between adjacent states, as shown in this factor graph representation of my system. Now, in addition to the sensor's global frame velocity, the state vector also includes the sensor's attitude and IMU biases so that we can accurately compensate for gravity and IMU biases. Now, I estimate these states by minimizing the cost function shown here over a sliding window of k successive Doppler measurements using Series Solver, which is a popular library for nonlinear optimization. Now, outlier measurements are another problem that could significantly affect the state estimate. This video shows a typical distribution of targets in an indoor scene with the radar targets colored by their Doppler measurement. The points in green are false alarm readings, a consequence of the AWR sensor's use of the constant false alarm rate detector. The Doppler measurements of these false alarms do not agree with the rest of the points in the scene, making them outliers with respect to the sensor model. There may also be non-stationary objects in the scene, like the person who's about to enter from camera right. We can notice that she produces a large number of targets that also do not agree with the rest of the scene. To ensure that these outliers don't adversely affect the state estimate, I use a maximum likelihood sample consensus step to explicitly detect and remove outliers before adding measurements to the optimization problem. Now, I compared my method to visual inertial odometry as implemented in the Intel RealSense T265 and LiDAR odometry using a Velodyne VLP16 with the LAMP odometry package. Ground truth, where available, was provided by a motion capture system. And for these experiments, the sensors were mounted on a hand-carried sensor rig, as shown here. I also ran tests in varying densities of fog to test each system's robustness to visually degraded conditions. Fog density was parameterized by visibility distance and varied from 12 meters to less than 6 meters. Ground truth was not available for these tests because fog interferes with motion capture in much the same way that it interferes with visual sensing. These plots show errors in the velocity estimates for a typical run with no fog. It's clear from these plots that the accuracy of our radar inertial method's velocity estimates is on par with other state-of-the-art methods when conditions are favorable. These plots show the state estimates from each method from a typical run in heavy fog. Now, even though ground truth isn't available, we can note that the visual and radar methods often agree, and LiDAR is usually the clear outlier. This suggests that LiDAR state estimation is affected much worse by foggy conditions than radar or vision, but without ground truth, we can't say definitively whether the visual or radar method was more accurate in these conditions. What we can do is run a test in a different set of conditions where ground truth is available. So to this end, I also tested my method against visual inertial odometry in darkened conditions. Now, these tests show that darkened conditions present a significant challenge for vision, but my system is unaffected. Particularly between 50 and 75 seconds here, we can see VIO has large deviations from ground truth, while radar does not. Now, I've established here that it's possible to use radar to accurately estimate the velocity of a sensor platform, but this is just one step in enabling mobile robots to use radar for autonomous navigation. In addition to state estimates, a mobile robot must be able to detect obstacles and map its environment. Occupancy mapping is a good candidate for this task, but using occupancy maps with radar has proven difficult for a number of reasons. First, commonly available occupancy mapping packages, such as Octomap, assume a beam sensor model, as shown on the left here. In this model, rays are cast from the sensor to each point in a scan, and the occupancy probability for a cell is decreased if it's traversed by a ray, and increased if it contains a ray endpoint. Now, this is a problem for radar, because radar doesn't cast a discrete set of rays, and it may detect multiple targets along the same ray. So to address this, I modified the ROS Octomap package with a volumetric sensor model as shown on the right. In this model, the occupancy probability for a cell is decreased if, the occupancy probability for a cell is increased if it contains a radar return, and it's decreased if it does not contain a radar return but is still within the sensor's field of view. Now, another difficulty with radar mapping is that a single object may generate several returns in the form of a multipath reflection. This is depicted in the image where the multicolored points are radar returns, and the white points are returns from a Velodyne LiDAR scanner. To address this problem, I developed a simple algorithm to detect multipath reflections and merge them into a single accurate return. This involves first running density-based clustering on the radar targets from a single scan. If all of the points in a given cluster occur roughly along the same ray from the sensor, the cluster is assumed to be a multipath reflection, and it's replaced by a single point, which is the centroid of the points in that cluster. Now, even with these improvements to the mapping method, radar scans still contain a relatively high number of spurious returns, so we cannot be very confident an individual radar return actually represents occupied space. This means individual radar returns do not increase the occupancy probability of their cell in the map by very much. This video shows occupancy mapping using my custom sensor model and multipath removal process. Now we can notice right away that the radar map is very sparse, and it also doesn't persist as the sensor moves away. We can also notice that some obstacles, like the car on the right here, are captured in a few occupied cells in the map, but other obstacles, like the pillar, also coming in from the right, go completely unnoticed. This is all a result of our low confidence in the individual radar returns. What we really need is a way to discriminate between true radar returns and noise. This would allow us to assign greater confidence to the points being fed into the occupancy map. And this is why I developed a learned model for discriminating between true and false radar returns. My method is based on the PointNet architecture. Now, the PointNet segmentation network, pictured here, is designed to accept whole, unordered point clouds as input and identify points in the cloud that correspond to particular shapes. This is nearly ideal for my purpose. Instead of identifying which points correspond to a particular shape, I train the network to identify which points correspond to noise and which are true returns. I also slightly modified the point net architecture for use with radar points. The original network operates on a vector of points defined only by their position in Cartesian space. It then performs a spatial transformation on those points to align them to a canonical orientation. Now, after this input transform, I concatenate a vector of the point's intensity and Doppler readings onto the point vector, changing it from an n by 3 to an n by 5 vector. The inclusion of this additional information improved testing accuracy by about 7 percentage points. Now, this video demonstrates the training pipeline for my point net architecture, along with some preliminary results. First, we can see radar points in red aligned with LiDAR points in green. Now, we use an automatic labeling procedure where radar points within a threshold distance of a LiDAR point are labeled as keep, and all others are labeled as discard. Next, we can see the labeled radar points with keep points in green and discard points in red. Now, these labeled point clouds are what is actually used to train the point net segmentation network. Now, the trained network is now shown here, classifying a live stream of radar points with keep points in green, discard points in red, and aligned LiDAR points for reference. These classifications appear to be subjectively reasonable, but the real utility of this method isn't demonstrated until we see its effect on the radar occupancy mapping method. This video shows the same radar mapping system we saw previously with the addition of the learned noise filter. And we can see right away that the map is much denser, and it also persists as the sensor moves away. It reliably captures salient obstacles, like the car we noticed before gets a lot more occupied points. The pillar that was missed by the previous mapping system, coming in right now, is represented in this map. And it also captures the floor and ceiling as well. This is clearly a big improvement over the original method, and I believe there's still a lot of room for improvement with the learned noise filter. With the training data available, it was able to classify keep and discard points with 82% accuracy in testing, but I believe with additional training data we could improve this further. Now, the radar mapping method was tested in varying levels of fog, and I compared its performance to visual mapping with the RealSense D435, which is a popular depth camera, and LiDAR mapping using a Velodyne VLP16. Now, the lack of ground truth in these experiments means mapping performance needs to be evaluated subjectively, but we can still draw some important lessons from these tests. Now, here we can see the performance of visual mapping in no fog conditions. Walls and other obstacles are reliably represented in this occupancy map. The positions of occupied cells are fairly stable over time, and we can pretty easily identify the structure of the environment here. Now, things change in heavy fog, however. In heavy fog, the returns from the depth camera are nearly all backscattering from the fog rather than actual obstacles. So, as a consequence, the maps created from these returns represent both obstacles and free space as occupied, and it's impossible to tell where obstacles are in the map, and the resulting map is essentially unusable. Here we run the same test using LiDAR. In no fog conditions, LiDAR does extremely well. It clearly represents walls and other obstacles. The positions of occupied cells are very stable over time, and the structure of the environment is pretty obvious. Now, in heavy fog, LiDAR has more powerful and focused beams that are a little bit better at penetrating fog than our depth camera. So we can still make out some walls and other obstacles in this LiDAR map. However, a significant number of the returns from the LiDAR are still backscattering from the fog rather than actual obstacles, and as a consequence, there are many cells in this occupancy map that are erroneously labeled as occupied. So it makes the structure of the environment much more difficult to identify. Radar, on the other hand, creates maps that are much more sparse than vision or LiDAR, but occupied cells in this radar map still pretty clearly correspond to occupied space in the environment, and the structure of the environment is still identifiable from these maps. Now, the advantage of radar mapping, however, becomes evident when fog is introduced. Occupied cells in the maps still correspond to occupied space, and there aren't additional cells in the maps that are erroneously identified as occupied, as there were with LiDAR and visual mapping. Now, it's certainly true that LiDAR and visual maps are more detailed and reliable than radar in conditions without fog, but LiDAR and visual maps are severely degraded when fog is introduced. Meanwhile, radar mapping performs the same with or without fog, so while it wouldn't be ideal to rely on radar alone when mapping an environment, it could be very useful to help a robot continue operating when it encounters fog or other perceptual difficulties. Now, this video demonstrates my full radar state estimation and mapping pipeline in use. The sensor pose, which is highlighted here, is estimated by integrating the velocity and orientation estimates from our radar inertial state estimator. We can also see raw radar returns projected onto the image stream from an onboard camera, and motion primitives evaluated by a simple local planner. Now we can see that the radar inertial state estimates are quite sufficient for local relative motion estimation, and the radar mapping system reliably captures the walls and door alcoves that we're passing. Put together, this system could be quite useful for local relative motion estimation and local planning tasks. The drift accumulated when integrating velocity estimates would likely make it less than ideal for long-range motion estimation, but I'll propose a solution to that later in this talk. Now, my work in radar state estimation and mapping has been fruitful, but it's also been held back by the AWR radar sensor that I'm using. The first problem has been the sparsity of point clouds returned by the sensor. It produces scans of at most 200 points at a rate of 10 hertz, and the main reason for this limitation is the AWR sensor's onboard memory, which constrains the number of points that it's able to process. Another problem with the AWR sensor is the constant false alarm rate target detector that it uses. It's very good for identifying discrete targets moving against a static background, but it's not well optimized for problems like odometry or mapping. Now, the most successful radar odometry methods so far have not used discrete targets as input. Instead, they use dense, high-resolution radar images created by mechanically scanned pencil beam sensors, like the image shown here on the slide. Now, although there is a high level of noise and other undesirable artifacts in this image, it certainly contains sufficient information for accurate two-dimensional odometry. Now, this level of density and detail simply cannot be matched by the targets generated on board the AWR sensor. Fortunately, we can get around this limitation by streaming raw radar signals from the AWR sensor and processing them on a separate computer where resource limitations are much less severe, and we can implement our own target detection or other algorithms that are specifically tailored for the problem we're trying to solve. Now, my method for processing these raw signals takes advantage of the AWR sensor's multi-input, multi-output, or MIMO architecture. A MIMO sensor has N transmitters and M receivers. The signals transmitted by the transmit antennas, phi sub n of t, are orthogonal, which in this case means that the cross-correlation between any two transmitted signals is 0. So, the transmitted signals combine and are reflected off targets in the environment. These reflected signals are received as y sub m of t by each receiver. But because the transmitted signals were orthogonal, we can split them back into the components that were caused by each transmitted signal. So for each set of transmitted signals, we get n times m received signals. Further, because the transmitted and receive antennas are spatially separated, there will be a difference in the phase of the received signals for each transmit-receive pair that it's dependent on the angle of arrival of that signal. This means that the received signals from each transmit-receive pair can be linearly combined to reconstruct the received signal from a particular direction. If we picture the large ellipse as the full field of view covered by each of the sensor's antennas, then the smaller ellipse here is a more focused and directed field of view obtained via beam re-steering. My signal processing pipeline reconstructs received signals from a discrete set of directions and runs a range Doppler FFT on each re-steered beam. The result is a dense radar image in spherical polar coordinates. Now, this video compares the AWR sensor's onboard signal processing with my custom pipeline. Now, first we can see the AWR sensor's pose and the sparse targets generated on board the sensor. For this demo, I move a large radar reflector within the sensor's field of view. The targets that correspond to that reflector are highlighted here. Now, these targets are quite noisy, but we can still pretty reliably track the position of the reflector as it moves in front of the sensor. However, these sparse targets give us almost no information about the environment apart from the location of that reflector. Now, to be fair, this is what the onboard target detector on the AWR sensor was designed to do, but this sensor is capable of a lot more. Here we can see the output from my custom signal processor. Each ray of points corresponds to a Fourier-transformed re-steered beam. Black points indicate low-intensity returns, and white points indicate high-intensity. Now, we can still reliably track the target in the output from my signal processor, but we also get information about the radar reflectivity of everything else in the sensor's field of view. We now have dense three-dimensional radar images. Now, these 3D images are going to be our jumping off point into full radar odometry. As I mentioned earlier, the most successful 2D radar odometry methods in the literature have relied on dense 2D radar images, such as the one shown on the slide. With the development of my custom signal processing pipeline for the TI AWR sensor, we now have a three-dimensional analog to the 2D images that have proven so useful for two-dimensional odometry. Now, my immediate goal here is to implement 3D radar odometry by detecting and matching key points in our 3D radar images. For this effort, I've taken inspiration from a recent paper by Barnes and Posner. Their method uses a UNet structure to predict key point locations, scores, and descriptors in 2D radar scans. It's trained in a self-supervised manner with no explicit labeling of the training data. The training loss is simply the error in the estimated relative pose between overlapping radar scans. So with this method, they're able to achieve odometry accuracy comparable to or better than stereo visual odometry. Now, I believe this method provides a good jumping off point for a similar method to detect and match key points in our 3D radar scans using a 3D UNet model. Now, apart from radar odometry, the other major component in radar SLAM is accurate and dense radar mapping. Although it may be possible to create usable maps from the key points from the radar odometry system described in the previous slide, I believe there's a way to further improve the density and detail of our radar maps. As I alluded to in the related work section, I believe techniques derived from synthetic aperture radar could be used to achieve this goal. This will essentially involve taking methods that have been in use for decades on air and spaceborne platforms and adapting them for use on lightweight robotic platforms. Now, in order to adapt SAR methods for robot perception, we need a much more general formulation of SAR than has been used in the past. In the standard method, a very narrow beam illuminates a small target area from a great distance with the sensor platform moving in an extremely predictable way. For robotic perception purposes, We'll use a very wide beam to illuminate arbitrary portions of the environment, which are relatively close to the sensor, and the platform's motion will only be predictable over a short time horizon. Thus far, no SAR method has been presented which deals with all of these problems. But this is another area in which the multi-input, multi-output architecture of our radar sensor is going to be useful. Remember, the MIMO architecture gives us the ability to digitally re-steer the radar's received signals, giving us crucial additional information about the direction of each return. So rather than illuminating an area of interest with a single wide beam, my method will be more akin to illuminating a large area with many narrow beams simultaneously. This concept is actually already established in remote sensing. It's referred to as MIMO SAR. But like other SAR techniques, it has not yet been applied to robotic perception. Now, combining the previously described radar odometry and SAR-based radar mapping methods will result in the first 3D SLAM system using radar as its primary sensor. Now, there's a number of ways one could go about this. The most obvious would be to use estimates from the radar odometry system to align radar scans and create SAR maps from those aligned scans. The biggest unknown here, though, is whether radar odometry will be able to provide pose estimates with sufficient accuracy to coherently combine our radar scans. SAR generally requires relative pose accuracy on the order of the wavelength of the radar sensor, which for the AWR sensor is just 4 millimeters. So even if this requirement can't be met by the odometry module alone, however, we may be able to use techniques referred to as SAR autofocusing to refine the rough pose estimates from the odometry module. Lastly, it may be possible to use these autofocusing techniques to jointly estimate the sensor's pose and the map in a tightly coupled structure. In this case, the method could get its initial guess at the relative pose between scans using integrated IMU measurements rather than the radar odometry method discussed previously. Regardless of the specific structure used, a SAR-based radar SLAM system will be a significant advance in SLAM technology. Such a system would provide accurate 6 degree of freedom pose estimates and dense, human-readable 3D maps. Best of all, it will be completely robust to the sorts of perceptual challenges that completely defeat the current state of the art in robotic SLAM, thus opening a host of fascinating new environments to exploration by autonomous robots. This concludes my talk. Thank you all so much for your time and attention. If you have any questions or would like to discuss parts of this with me, feel free to get in touch on LinkedIn or on my personal website. Thank you so much. Goodbye.